This is the third in a series of 3 seminars looking at the Xilinx RFSoC. In the first seminar, we looked at the actual RFSoC technology. We looked at the A to Ds and D to As integrated right on the FPGA. Then we moved on to a small form factor module that uses the RFSoC and how this small module allows us to deploy in all different environments in different form factors, and also allows a path to doing custom development for special environments or applications that can't use a standard form factor. In the second seminar, we looked at the FPGA IP and software development environment. We looked at Xilinx's Vivado tool suite, we looked at the Navigator FPGA design kit, and with it, we took a factory installed design and we modified it. We added a new IP core that allows us to monitor the traffic, the data traffic, through a specific part of the IP. We took that, we compiled it, created a new output image, brought that image into Xilinx's Vitis tools, and there we used the board support package, the Navigator board support package, to create a new kernel, including now support for the new IP that we installed. Went in, modified the software, and ultimately created and ran our application with the modifications. And through those first 2 seminars, we were tracking a path from a design concept all the way through implementation and ultimately deploying it in your final application. In this seminar, we're going to look at a requirement that's fairly common in many applications, and that's multi-channel synchronization. We're going to look at why you might need it, how it's implemented, and specifically how it's implemented in the RFSoC. So first, let's look at applications that don't require multi-board synchronization. An example might be a multi-channel transceiver for communications. In this case, each channel receives, demodulates, or modulates, and then transmits pretty much independently. And this is what it looks like. I've represented this system with a single channel with an A to D for receive and a D to A for transmit. Now there's some signal out there that you're trying to receive. It's probably a communication signal again in this system. That'll go to possibly a digital down converter or a DDC. The reason for that is that allows you to take the entire spectrum and you can tune it in to a specific band that you're interested in. Now in this system, there may be, in addition to demodulation, there may be decryption, there may be a secure band that people are communicating on, but ultimately that'll get decoded and it can go out to a human operator. So the human operator would hear the signal, listen to it, and possibly respond back. Then that signal might be encrypted and then sent back through the digital up converter. That'll translate it to a frequency that can be transmitted, and at that point it will be transmitted out. And that completes a complete loop from A to D through D to A with a human operator. Now in this system, there could be multiple channels. There might be another channel listening to a different band, and maybe a third channel listening to yet another band. But in this case, each one of these is really operating independently. So the fact that the A to Ds and D to As and the information that you're getting in each one of these cases from that waveform really doesn't need to be synchronized. It doesn't need to be locked together for any reason. Now, a common technique that's used in a lot of systems, it could be in communication systems or it could be in radar or electronic countermeasures. 5G uses it, any kind of cell communication, is beamforming. And in its simplest sense, beamforming is based on constructive interference. So to just demonstrate this, and I think most people know how this works, I have 2 antennas that are set up here with amplifiers, and I'm going to create a source which is going to generate a wavefront. When that wavefront hits the antennas, each one of these will have a signal that it's receiving. Now, if you add the 2 signals together or sum them, the resulting signal is greater in the amplitude than each of the individual signals. And that's because the 2 signals are working constructively to add together and create that larger signal. And this really only works because the 2 signals are in phase with each other. They're effectively in the exact same space and time. But if you look at this and you offset one signal, in this case, let's offset it by 180 degrees or as close as we can to it, what happens is when you add the 2 signals together, they negate each other and it reduces the signal, actually canceling it out. So this is an ideal situation, but the reality is more like this picture. Let's say we have 8 antennas, they're all in an array, and each one of those is going to an A to D, which is representing the receiver. I'm using a satellite image here as the representation of the signal source. So the satellite generates a waveform, it hits the first antenna, and now I'm showing that signal on that wire. Now, I'm kind of cheating here. I'm using the wire between the antenna and the A to D, not just to represent a place to show the signal, but I'm also using it to show that signal in time. So when that wavefront hits the second antenna, it's a little bit further out in time, and the second waveform you can see is kind of offset from the first one. And as that wavefront hits each of these different antennas, what you're seeing is that each time you're getting that signal on that wire, it's actually a little bit further out in time. So they're all offset based on the distance between each one of these antennas and when that wavefront hits it. Now I'm going to extend that line again in this case and also use it to represent time. As each one of these A to Ds converts that analog signal to digital, it's going to happen at the same time from when the A to D receives it to the output, but since each A to D is receiving it slightly later, the digital representation of all these signals is also going to be offset as you go through each channel. Now the trick here again for that summation or for that constructive interference is to have all of these lined up perfectly. So one way to do it is to use a digital down converter or a DDC. And with that, the output of that, you can adjust the phase. And with that, you can line up all of these signals. So now they're all phase aligned. You can bring them into a summation stage where all 8 of these signals are summed together to produce a greater signal on the output. And the only reason why this worked was because, again, we can offset that phase, but you also need to have all the A to Ds perfectly synchronized. What that means is that all of the 8 A to Ds need to be locked together effectively. And the reason for that is that phase adjustment really needs to be set for each channel, and you can't have the A to Ds kind of walking around. So if all the A to Ds were running at the same sample rate, but let's say they were not synchronized, they were not locked together, what may end up happening is as you continue to sample, you'll find that the delay between the analog signal and its digital representation can move around. And that really makes the summation difficult because, again, you're phase adjusting against a moving target. So what I've shown up to this point is a pretty simple linear array of antennas, but phased array antennas appear in all different shapes and forms and sizes. This is a representation of a experimental 5G antenna that would be used in 5G communications. It's fairly small. This would be on, let's say, a mast or on top of a building. This next picture shows a pretty dense phased array antenna in the front of an airplane or of an aircraft. And this is very commonly used in both commercial and military applications. And this last picture is an antenna array that the US military used in Afghanistan. And you can tell by its size and also the number of channels, this is a massive antenna. So what ends up happening is you end up with anything from small antenna counts all the way up to these large antennas. And what ends up happening too is that as you bring them into smaller places like the nose of that aircraft, getting all those A to D channels and D to A channels right behind that antenna array becomes critical. So that's why the RFSoC is such a good solution. Each one of those RFSoC chips can do 8 channels of A to D and D to A. And because of the small form factor module that we have, you can actually put many of those modules in a custom enclosure and position them right behind the antenna array. In addition to the density and being able to fit all these channels, the other key requirement, of course, is having them all be synchronized, having all the A to Ds and D to As locked together effectively. So that's what this next section is about. Within the RFSoC architecture is something called multitile synchronization, and that's what I want to show in a little more detail. So I've used this image in the previous seminars, and on it you can clearly see the processor subsystem, the ARM processors, general purpose and high-speed connectivity, the resources that you'd expect to find in an FPGA, the fabric, the DSP slices, the memory, and of course this highlights the RF signal chain, which are the A to Ds and the D to As. So now what I'd like to do is make some room and move out all the components I don't need and really just focus on the RF signal chain. The 8 A to Ds and D to As aren't all independent. Actually, they're in pairs, or what Xilinx calls tiles. Each pair of A to Ds is in a tile, so there's 2 A to Ds per tile, and each pair of D to As, or 2 D to As, are in each tile. For the purposes of going through and describing what's happening inside each one of those tiles, I'm going to focus just on the A to D tiles. Now, this is the same whether you're in the A to Ds or the D to A tiles, but I just want to make some more room and just focus on the A to Ds for now. So if I expand that tile out, you can still see the two A to Ds, channel 1 and channel 2. I'm going to draw just as a symbol two sine waves coming in. Those are going to be the inputs to the channel. And the first signal I want to define in this tile is the A to D sample clock. The RFSoC allows you to come in with the full sample clock rate. So you can run the 5 gig A to Ds coming in with a 5 gigahertz clock. Or you can actually come in with a slower clock and use the PLL to bring you up to the desired clock rate. You could also divide the clock at the front end to get a lower clock rate. But within each tile, whether it's A to Ds or D to As, the two converters in each tile run on the same clock. Now, you can send different clocks to different tiles, but within a single tile, the A to Ds or D to As are running at that same clock rate. That A to D clock is also passed outside of the tile into the fabric as a reference clock for the fabric behind it. The next thing I want to draw on the block diagram is the output of the A to Ds. These are the parallel outputs. I'm calling here the data path as the interface to the A to Ds, and then that feeds into the FIFO, and the FIFO sends the data out into the fabric. So that's the main signal path for each of the A to D channels. But now let's add some of the signals you need for multi-tile synchronization. The first is sysref. Sysref, I think, is borrowed from, well, the term is borrowed from what is used on JESD serial interfaces, but the sysref here is slightly different. The sysref provides a signal to the sync logic. Each tile has a delay circuit prior to the sync block, and that allows you to better match the sysref across all the different tiles. The sync signal is then fed into the FIFO control block. There's another signal coming in called the axis stream clock. Now, this is actually a clock that's used to ultimately clock the fabric, and that signal goes into the FIFO control block also. A third signal going into the FIFO control block is the A to D sample clock. Those three signals combined give you the FIFO control output, and that's used to clock the FIFOs. Now, one more signal you need to create is a registered version of the sysref that's actually being registered to the axis stream clock. So those signals go into a flip-flop, that's where it's registered, and out of that you get what's called the PL sysref or the programmable logic sysref. That's fed into an IP sync state machine, which is actually not in the A to D, D to A section, but in the main fabric of the FPGA, and that's brought in to clock the back end of each one of these tiles. So those are the main signals you need to synchronize multiple tiles. I'm going to add 2 more tiles to this to give you a total of 6 channels. I could have added a 4th to give you the 8 channels. And it's basically the same thing on the A to Ds or D to As. I just want to connect the IP sync state machine outputs into each one of the back of these tiles. And that's pretty much the whole circuit. So just to review what we have here, there are 3 signals that are required for multi-tile synchronization. You need sample clock, you need sysref, and you need axis stream clock. And all 3 of these signals are coming from outside the FPGA. That's why they're coming into the left side, into the fabric, or in this case, right into the PLLs. The other thing is that this was all taken from a product guide. There's a much better description than anything I've been able to give here in that product guide. So it's the Xilinx Logicore IP PG269. And if you go to the Xilinx website, you could just do a search and find it. In there, it also gives you information about the timing relationship between these signals. You know, I said before, the sample clock can be running at the full sample rate. The axis stream clock is typically running at the fabric rate, which is like 500 or 600 megahertz, and the sysref is being clocked off that. But all the relationships between those signals is listed in that PG269. Also, the sequence of events you need to go through to configure this must be done in the right order. And there's also an example of how the software can be written to synchronize all of the cores so that everything remains locked together. So now I'd like to go through a few slides to show how all of this works together. The first slide is showing our model 5950. This is our 3U VPX RFSoC. And what you'll notice on here is the block diagram. This basically shows everything that's on that board, including the RFSoC and all the circuitry around it. But there are a few signals that I want to highlight, and they're right here. The sample clock, the sysref, and the axis4 stream clock. These are the signals we just talked about. Now, the reason why these are here is, again, to support multi-board, in this case, synchronization. These signals come in through the VPX backplane. There's 2 more signals we added to that, which is sync and gate. I didn't talk about those, but I'll explain what they do in a minute. You don't need them, but they'll certainly help you with the overall synchronization in your application. And then there's a rear transition module that we use with this 3U VPX board. That rear transition module actually has a connector on the back that allows you to bring these signals into the board. So the product that complements the RFSoC board is our Model 5903 Quartz synchronization board. This allows you to synchronize up to 8 Quartz RFSoC products, like what I just showed you, the 5950. You can synchronize up to 8 of those. This board generates the sample clock and all the associated clocks that you need to do multitile synchronization. So that's all generated locally on this board, and it synchronizes all the channels on all the boards to single sample accuracy. And again, that's critical for doing things like beamforming. This is a block diagram of the board. I just want to go through a couple of the input signals. You can bring in a reference clock. Now this board generates the sample clock locally, which can just free run, or you can have it running off this 100 megahertz oscillator. But you could also bring in a reference clock, and let's say a 10 megahertz reference, and you can have the board lock its sample rate to that reference. There's also an external sync, which allows you to do things like reset all the local oscillators and the digital down converters and all of the FIFO circuitry. There's also an external gate in, which allows you to send a synchronized gate signal to all the different boards. There's actually 2 gate signals, but in this configuration, we're only using 1. Within the board, we're generating the signals we said we always need for doing multitile synchronization. We're generating the clock, the sample clock, we're generating the sysref, and we're generating the axis stream clock. In addition, again, we have the sync and the gate. All of these signals are being sent through the front panel through 4 multi-pin connectors. So these are all identical copies of those signals. And you can see right there on the front panel. This model also has a rear transition module. The rear transition module allows you to bring 4 more exact copies of those signals to the back of the board. And again, this gives you up to 8 total synchronization outputs, which allows you to synchronize 8 Quartz products. So let's take a look how this works in a typical 3U VPX air-cooled chassis. The first thing is you have the 5950. This is the RFSoC. We'll plug that in. There's the rear transition module. We'll plug that in. And again, the reason why the rear transition module is important is the sync connector is on the back. Then we plug in the 5903. That's our synchronization board. And we plug in its associated rear transition module. With that all installed, you can see the sync connectors on the back on the rear transition module. We can use a cable to connect the sync board into the 5950. So not very exciting. That's a 1-channel synchronized system. But when we add some more 5950s and RTMs, it gets a little more interesting. Now we can wire it to have all 4 boards be synchronized, single sample accurate across all A to Ds and across all D to As. In addition to the rear transition module, there are still 4 unused connectors right now in the front. So we can put in 4 more 5950s, 4 more RTMs, and we can use those front connections to wire up 4 more boards. That's how I get a total of 8 boards being synchronized in this system. To keep everything synchronized, we're using 8 precisely length-matched cables to make sure that the signals coming from the sync board are getting to each of the 8 RFSoC boards at the same time. This looks a little different in a conduction-cooled chassis. In a conduction-cooled chassis, you don't have the option for RTMs, so you can't use those for doing the synchronization wiring. What typically happens is those synchronization signals are routed right within the copper of the backplane. And if you remember, the 5903 has 4 outputs coming out the back, so you're looking at 4 5950s being synchronized. This is pretty typical in a conduction-cooled environment. Another option is to use a cabling system from a company called Meritech. Now what Meritech makes is a shroud and cables that go on the back of the VPX backplane, and these shrouds go over where the RTM normally would go. And you can see in the first picture the cables are breaking out into individual SMAs or some kind of coax connectors. But Meritech also makes precision length matched cables that allow you to connect between slots. And in that third picture you can see a detail of what the connectors look like. So the way this works is you would install the shrouds on the back of the slots where you want to connect the Meritech cabling, and then you'd run the cables across. Again, these are all matched length cables, and this gives you your sync cable connection. And this is convenient because you don't need a custom backplane, so it's great for doing development work, but also the Meritechs are pretty rugged and can be used for deployed applications also. So the last thing I want to show is an actual demo of the RFSoCs being synchronized. This was done by Paul Mezabov, who's our VP of Engineering, and I videotaped it. It's just easier to show it that way. And what he's doing is he's setting up the 5950s and the 5903 and going through all the steps required to do the synchronization and then showing the output both on the A to Ds and the D to A synchronized. So let's take a look at that.
Hi, this is the setup that we're going to use to demonstrate the Model 5950 synchronization between two boards using the Model 5903 synchronizer board. I've got a signal generator generating a 420 megahertz continuous sine wave output through a power splitter, and that is the output of the power splitter is driving channel 1 of each of the 5950s. That'll be used for the ADC synchronization demonstration. And then, of course, channel 1 of the outputs of each 5950 goes to this oscilloscope, and that'll be used to demonstrate the DAC synchronization. If we go around the back to the back of the chassis, you can see how we've got things interconnected. The rear transition module for this 5950 actually has a USB connection to the 5903 on the front. We'll show that to you. And then, of course, we've got two Ethernet cables, one for each 5950 that is going to our office network. And here are the two synchronization cables going into the sync inputs of the rear transition modules. Let's follow that around to the front. And you can see the two synchronization cables going into two ports of the front panel of the 5903. And that is the setup. Now what we're going to do is we're going to log into this system from a remote office using Secure Shell, and you'll see a video depicting the actual configuration and operation of the system. I am going to demonstrate how to synchronize two Model 5950 RFSoC boards using the Pentec Model 5903 synchronizer board. I am using Navigator BSP revision 1.11, and you can see as I look into the directory containing the example MB acquire, which stands for multi-board acquire, there is a README file which is very important to read. The README file describes how to set the system up by interconnecting the USB and sync cables properly. It also describes a very important item, the communications server. This is a program that is compiled and run on a host computer that is on the network with the 5950s, and its purpose is to command the 5950s in the proper sequence during their clock initialization so that they can be ready for synchronization. The communication server relies on a configuration file that specifies the executable program, the initialization file, and the IP addresses of the boards. The designation of a 5950 as master simply means which board is controlling the 5903 via USB. Ultimately, both boards receive their clock and sync signals from the 5903. You can see the board initialization files contain the IP address of the board and the COM server. It also specifies a unique output file name and location. In the ADC sync example, the loop parameter is set to 1. This causes each board to execute a single acquisition. After completion, the boards notify the COM server they are finished, and the COM server exits. Let's give this a try. After launching the COM server, there is some passage of time while each board completes its initialization sequence. As I mentioned before, when complete, the COM server exits. And there it goes. Let's take a look at the results. Each board writes its file to a file server on the network. I have written an octave script to read these files and plot them to show synchronization. The script also calculates the phase and ultimately time difference. You can see the nice alignment between the two waveforms, and the script shows about 27 picoseconds of time delay between channel 1 of each board. Given the 4 GHz sample rate, it is clear that this time delay is much less than the 250 picosecond sample period. Now let's demonstrate the DAC synchronization. The COM server configuration file points to the executable file MB DACwire. This example program has been compiled to demonstrate a triggered chirp waveform. This will make it easy for us to see the synchronization in both phase and trigger point of the two boards. Also, an examination of the two 5950 boards initialization file shows a loop value of 0, meaning the execution will continue indefinitely until the COM server tells the boards to abort the program. Takes a little time to initialize the cards. And the COM server will stay here until the user presses A to abort, in which case the COM server will then notify the two 5950s to exit their program. Here is a video of the oscilloscope connected to the 5950s. You can see the grade alignment at the beginning of each waveform.
So I think that was my last slide. I welcome you to visit www.pentech.com. We have a lot of information up there, plus the manuals are available for most of what I showed you today.